Okay. Hello friends, my name is Hemant Sharma. I am Assistant Professor in Mechanical Engineering Department, Faculty of Engineering and Technology, Rama University, Mandhana, Kanpur. So the topic of our today's presentation is Bernoulli's equation and its applications. Right? We should look at the assumptions first. So there are 4 to 5 assumptions of the Bernoulli equation. First of all, it is an energy conservation equation. Number two, the flow is steady. So by it v means that there is no variation with respect to time, right? So that is curl by curl t is equals to 0. Means if the fluid is flowing with some velocity, right, at a particular instant of time, let's say in the morning it was flowing with a velocity of 10 meter per second, and in the evening, right, it was again flowing with a velocity of 10 meter per second. That means there is no variation with respect to time, right? So the second assumption is the flow is incompressible. So by the word incompressible, we mean that the density change is 0, right? There is no change in density. So that's why it is written d rho equals to 0. You can take the example of a water, right? Whilst now in the further slides we'll see that the water water has a density of 1000 kg per meter cube, right? It is a constant density fluid, so there will be no change in its density. Then third assumption would be the flow is ideal or inviscid. That is, the viscosity is 0. Ideally, viscosity is not 0, right? But we are considering here as 0 because viscosity in fluids, it signifies losses, right? But here we are considering that there are no losses, which is not practically possible, right? Losses exist, so that's why. So it's another assumption that the flow is ideal or inviscid. That means there is no viscous forces in the fluid, right? And the fourth and the last assumption, the fluid is irrotational. So by the word irrotational means that there will be no change that the net rotational change of the fluid particle is equals to 0. We'll see that omega z equals to 0, right? We denote rotation with omega. So omega z in a particular direction is 0. So these were the assumptions of the Bernoulli equation. Let's move to the statement. As we said earlier, that it's the sum of the pressure head, kinetic head and datum head is constant. So the pressure head plus velocity head and datum head at the inlet, it is same as that of the outlet. And in the next line, but mind that the second equation, right, it is only meant for the ideal fluids where there is no viscosity change, right? Means there is no viscosity here, there are no losses here, but in practical losses exist. So that's why we will include the losses, and we will add HF in the right hand side in the third equation. You can see, right, here HF signifies head loss due to friction, right? Head loss due to friction, right? And these head losses, they will be calculated with the help of Darcy-Weisbach equation or Hagen-Poiseuille formula, right? Darcy-Weisbach equation is a very popular equation for calculating the head losses in the pipes. So moving on, applications of Bernoulli theorem. Bernoulli theorem has 3 main applications, namely number 1, Venturi meter, which is used to measure the discharge or average velocity. Number 2, orifice meter, which is used to measure the discharge or average velocity. And number 3, pitted tube, right? It's a very catchy word, pitted. It is a L-shaped tube which is used to measure the instantaneous velocity. Instantaneous velocity means the velocity at a particular point in a fluid flow. Whereas Venturi meter and orifice meter, they also measure velocity, right? But they measure velocity at a particular section in a pipe. Whereas pitted tube measures instantaneous velocity, that is velocity at a point in a fluid flow, right? So these are the three applications of the main applications of the Bernoulli theorem. Now let's discuss them in detail. Venturimeter. So basically venturimeter is a converging throat diverging device which is used for measuring the flow rate of a liquid. As you can see from the construction, that at the area 1, at the inlet, it is converging, right? At point 2, point 2 is point 2 is known as throat area, and point 3 is known as the diverging area. So as you can see that we have fitted one U-tube manometer, right? So basically when the fluid will flow through the venturimeter, so there will be, due to the constricted passage at the point 2, that is due to throat पे क्या है, we have very less area, right? Since the area is less, from the continuity equation we have the velocity will be more, right? The velocity will be more, and if we go to the Bernoulli equation, which states that the sum of pressure head plus kinetic head plus datum equals to constant, right? Neglecting the datum here, if the velocity at point 2 is more, then the pressure at point 2 will be less, right? And the pressure at point 1 will be more. So that's why it will push the liquid towards point, right? So that's why there is an increase in the limb difference, that is height h in the at point 2, right? Point 2 पे आप देख लो level पानी का बढ़ा हुआ, because the water which is flowing at state 1, it has higher pressure, so it will push the manometric liquid towards point 2 and it will raise its height. Clear? And in the adjacent diagram you can see venturimeter, right? Its construction. So basically it's a converging throat diverging section, right? Converging throat diverging section which is used to measure the flow rate, that is discharge through the pipe, by measuring the manometric limb difference. So basically, and from the discharge we get average velocity, right? Everyone knows that discharge is equals to the product of area into velocity. And then coming to the working principle, it works under the principle of Bernoulli's equation and continuity equation, which I have explained just now, according to which by reducing the cross-sectional area of the flow passage, a pressure difference is created, right? By reducing the cross-sectional area of the flow passage, कहाँ cross-sectional area reduce किया हम लोगों ने? At point 2, throat पर, right? At the throat section, a pressure difference is created, and the measurement of this pressure difference enables us to measure the flow rate through the pipe. And this pressure difference is measured with the help of a manometer, right? You can see the figure that at point 2 area is less and A2 is less than A1. So from the continuity equation, since the continuity equation, it says that product of area into velocity is constant, right? So velocity will be higher at point 2, and from the Bernoulli equation, which is the energy conservation equation, we will get pressure at point P1, it will be higher than at pressure point 2. Coming to the working equation which is used, now we will see the equation which is used for calculating the discharge in a venturimeter. So here we can see that by applying the Bernoulli's theorem at the inlet and the throat section, the relation for the flow rate can be derived, right? What we are going to do is that we will apply the Bernoulli section at point 1 and at point 2. Point 1 is the upstream point, right, converging point, and point 2 is the throat point. So here we will apply the Bernoulli equation. We started from the Bernoulli equation, right? We substituted the velocity head in terms of small h, applied the continuity equation, substituted the value of v1 in terms of v2, right? And then we get the value of v2 at the end. Now from here, so as you can see that we derived the value of coefficient of discharge. It basically it lies in the range of 0.98 to 0.99, right? You can read it in detail in the book, right? What does it signifies? There are three in the R.K. Bansal book. There is a heading called hydraulic coefficients. From there you can read in detail that. So lastly, you can see the applications of it. It can be used, venturimeter can be used for measuring the flow rate of water, gases, suspended solids, slurries and dirty liquids. Number 2, it can be used to measure the high flow rate in pipes which are having few diameters. Number 3, it is used when we are working with small pressure head, right? The pressure head is not very high. So some of the applications, and the limitations are, it is a costly device, it requires maintenance, right? So for the, it cannot be altered for measuring the for measuring the flow rate up to a wider range, right? And it also cannot be used, it cannot be used where there is a space limitation, right? Because it's a, you have to fit it in the pipe, it's a converging flow diverging section, right? No doubt it has got initial cost, the initial cost and installation cost, they are very high. So these are some of its limitations. Clear? So in this today's lecture, we learnt about Bernoulli's equation, right? And its Bernoulli's equation, its assumptions, where it is, its mathematical form, venturimeter, how to derive the expression for the discharge for the venturimeter, its applications and limitations. So if you have any doubt, you can mail me at hemantsharma.fet@ramauniversity.ac.in, or alternatively you can mail me at hemant9847@gmail.com, right? Thank you.